Hi there, my name is Charles Wasfani Sipa. Welcome to another presentation on elements of matrix analysis. In this case, we're going to look at matrix diagonalization. Usually, there's sometimes a need to transform matrices to simpler forms in order to get simpler models of systems. One such transformation is to transform a given matrix to its diagonal form, which is usually considered to be the simplest form of the transformed matrix. And the process of doing that is called diagonalization. This is what we're talking about. And the term used for the simplest form of such matrix is called canonical form. In other words, here we're going to discuss what you can call reduction to canonical form. Canonical is just another fancy word to maybe say the simplest form of such a given matrix. So like I've said, this transformation actually done in order to get simpler models of systems. So where do we start? Let's say A is a matrix of n by n. So what we've already seen is that if we've got a matrix of n by n, for it we can obtain n eigenvectors, let's say E1, E2, up to En. Now we recall that if we're, let's say we're in Rn, this E I vector is actually a column vector of the form EI1, EI2, up to EIN. I stands for n of numbers 1, 2, up to n. So we've got that. So having these vectors, what can we do? One interesting thing we can do is that we can decide to pack these vectors into a kind of a matrix, E1, E2, up to En. Now recall that each one of these vectors is of this form, which means this is actually an n by n matrix, which is E11, E12, up to E1n. Second row will be E21, E22, up to E2n. And going down, we can go up to row n, En1, En2, up to En. So you've got a matrix like this, which results from packing the eigenvectors into one packaged matrix. And then this matrix actually is going to be given a name M. M standing for modal. In this case, this is what we call a modal matrix. So a modal matrix is a matrix which comes as a result of packing eigenvalues into one package, which is a matrix. Now, on the other hand, we know that these eigenvalues correspond to eigenvectors. So now we know that this M is modal matrix corresponding to matrix A. So we associated with A also got n eigenvalues, let's say lambda 1, lambda 2, up to lambda n. So what you can do also, we can actually, using these eigenvalues, you can actually create a diagonal matrix associated to this modal matrix as follows. That diagonal matrix will be also a square matrix, n by n matrix, which will be lambda 1 in the first row, accompanied with zeros, then 0, lambda 2 in the second row. In other words, all the eigenvalues are going to be situated along the principal diagonal. Then we've got here lambda n. Then this is a square matrix. So this matrix, which will create this way using the eigenvalues corresponding to the eigenvectors here, is going to be called a spectral matrix, and is denoted this way. And this is what we call a spectral matrix. So this spectral matrix is associated to the modal matrix corresponding to A. So the three matrices are actually linked by the relationship. We got that these are eigenvalues corresponding to A, and these are eigenvectors corresponding to these eigenvalues. Now, having this concept of a modal matrix and a spectral matrix, what can we do? But first of all, let's look at an example which we saw before. Before, we had the matrix A, which had entries 1, here minus 1, 2, 1, 0, 1, minus 1. This is an example we saw before, and we computed eigenvalues for this one. The eigenvalues were E1, which is equals to 1, 3, 1. I'm using T here for transpose because I'm lazy to write this vector as a column vector. Then I write it this way. You should understand that when I put T there, I'm actually talking about column vectors 1, 3, 1. Then the second vector was E2, which was 3, 2, 1. Then you're going to use transpose. And the last vector, E3, was equals to 1, 0, 1. Now, in the set of eigenvalues which we had here was lambda 1, which was equals to 2, and lambda 2, which was equals to 1, and the lambda 3 was equals to minus 1. Now, if we want to obtain a modal matrix for such a modal matrix corresponding to A, in this case, we will have to take these vectors as column vectors to create M, which is our modal matrix. Then in this case, we're going to take this one as a column as 1, 3, 1, followed by E2, which is 3, 2, 1, and lastly 1, 0, 1. Now this is our modal matrix. Now to get to corresponding diagonal matrix, the spectral matrix, which is denoted this way, we need to be very careful to correspond to this column, and the following eigenvalue, which is 1, correspond to that column, and lastly minus 1 correspond to the last column there. Now when we're going to come up with this spectral matrix, we need to put the eigenvalues exactly in the same order. In this case, let's do it this way. Let's put the spectral matrix underneath here. Then it's going to be our spectral matrix equals to, then like the first row here corresponding to 2. We'll make sure that the first row here on the spectral matrix contains that eigenvalue. Then you know that the rest are going to be 0 here. Then 0 and 0. Then when you come to the next second row, then that eigenvalue 1 is going to appear in the diagonal of the second column. Then we're going to have the last one appearing in the third row, in the third column. In other words, looking at the modal matrix and the spectral matrix, we must understand that this value, eigenvalue, is this as its corresponding eigenvector. Similarly, this value in the second column is this vector as its corresponding eigenvector, and similarly this one in that. Then if we're instructed to obtain both the modal matrix and the spectral matrix, if we swap, or if we don't put this in the corresponding way as it is there, then our answer is going to be considered to be not correct. So it's very important to make sure that you keep the same order here. Now, the next step is to see how the modal matrix, the spectral matrix, is actually related to the diagonalization of the given matrix A. Let's say we've got the modal matrix M. In this case, we've seen that the modal matrix consists of the eigenvectors, let's say n of them, and we've got the matrix A whose eigenvectors are given in the model. So it is clear now, if we apply or post-multiply A by M, this is exactly the same as multiplying E1 by A and multiplying E2 by A up to multiplying En by A. Now, because these are again vectors of A, we expect this to give us lambda 1 multiplied by E1 and lambda 2 multiplied by E2 and lambda n multiplied by En. And the good reason for that is that these are eigenvalues corresponding to matrix A. Now, if we look at this multiplication, we can see that this here, it will be the same as multiplying the modal matrix E1, E2, E3, the modal matrix, by the spectral, which will be consisting of the, along the diagonal, consisting of lambda 1, lambda 2, up to lambda n. Now, what we know, and we've seen before, is that eigenvalues are actually linear independent. So if these are linear independent, that means that M is a non-singular, in a non-singular matrix. And I hope you've made this non-singular, the term non-singular matrix in studying your textbook. This means that the determinant of M is actually different from 0. And having determinant of M different from 0, that guarantees us that M inverse exists. Now, if we've got M inverse, and starting from this equality of these two, let's say we've got A, M equals to M by the spectrum. Now, if we have got M inverse, we can pre-multiply here both sides here by M inverse. We can have this M inverse multiplying A multiplying M equals to M inverse multiplying M multiplying the spectrum. But what we know is that if we multiply a matrix by its inverse, we get the identity. It is the identity is called M inverse multiplied by M, which we have here. But now the identity multiplied by any matrix gives us the same matrix. Then this is the identity multiplying the spectral, we get here the spectral. In this case, this spectral is a diagonal matrix. What does this mean? And then what we observe here is that multiplying A or sandwiching A this way between the inverse of the modal matrix and the modal matrix results in a diagonal matrix. In other words, this process here becomes the process of diagonalization of the matrix A. So as we can see, what we need here is we need to know how to determine the inverse of a matrix, given that we know that the determinant of the model matrix is non-zero, which is guaranteed by the fact that the eigenvectors are linear independent. So at this point we can say we've got one of the approaches which can be used to reduce matrix A to its canonical form, in this case, which is a diagonal matrix. At this stage, we've seen how we can use the eigenvectors, eigenvalues in the process of diagonalizing the given matrix A to obtain its canonical form, which comes in a form of a diagonal matrix, which is called the spectral matrix. And this is important to know how to do, which, and as you can see, is going to be based on also on knowing how to determine inverse of matrices, which we've seen before. Otherwise, for now, thank you for listening.